And welcome to Climate Chat. I'm your host, Dan Miller, and with me is my co host, Leon Simons. And today we'll be talking about asymmetries between the warming that's going on in the northern and southern hemisphere. But before we jump into that, we have some programming notes. The first is that next week, October 19th, there will be no Climate Chat program. I have a memorial service to attend to, and Leon's not available, so there will be no program next week, October 19th. However, the following Sunday, October 26th, we're going to have climate scientist Andrew Dessler, and he wrote a rebuttal to the Department of Energy, quote, climate report, which was written by climate deniers. And he did a very in-depth analysis of that report and why it's wrong. And so that should be actually quite fascinating. And speaking of fascinating, the following Sunday, November 2nd, we're going to have Wim Carton, who is the co-author of a new book called The Long Heat. And to kind of summarize it a little bit, it's Wim and his co-author are sort of anti-capitalist and think that the capitalism is what's fueling climate change. And it's also against solutions like solar radiation management, partly because he thinks that's delaying other action, but we'll get into the details of that when he's on November 2nd. And following that, November 9th, Jigar Shah, former head of the Department of Energy Loan Office under President Biden. He's also the co-founder of Generate Capital, and I worked with him on something called the Carbon War Room long ago. So he's been involved in climate for a really long time. He's going to be able to give us an insight into what it was like inside the Biden administration in terms of fighting climate change. And in addition to that, not on Climate Chat, but Leon, our co-host Leon Simons, is giving 3 keynote addresses in the near future. Leon, can you tell us about that?
Yes, hi Dan. Let me just share this. Show it. Yeah, hi. So I will be this month. I will give 3 keynote addresses. Indeed, one will be this week, and everyone can attend. You can register online through preventingtodegrees.org at a global online conference about the global heating emergency. And this will be, of course, as a lead up to the next COP conference, where we'll be talking about accelerated warming and how we can still prevent 2 degrees of global warming within decades. And then later this month, on October 21, ahead of the elections of our Dutch government, I will be speaking at a climate conference in the Nieuwspoort. Most people don't know about that, but it's in The Hague, and it's to inform politicians, policymakers, and the public about climate change and why it's important to take care of adapting to the rapid changes, of course, and faster mitigation, and not just because of warming, but also because of course, all the other impacts, like migrants coming from the south to the north, or the Dutch becoming migrants ourselves if we let global sea levels rise by multiple meters this century. And then the end of the month, I will be speaking at more climate resilient cities 2025 conference in Bratislava. So I hope to see some of you there. Okay.
So, so the online one in English is preventing2degrees.org.
Yeah.
The other one, is it online? The other one, the Dutch one, or is it
the Dutch one? Yeah, you can register. You can watch it online, or you can come to the Nieuwspoort, and that's mainly for media and for politicians.
And that's going to be in Dutch.
Yeah, that will be in Dutch.
And then the last one is in person more climate resilient cities 2025, and in Slovakia. Okay.
Yeah, and it's also, you can also attend online there.
I'll try if I can during the talk to add the links to the show notes while we're at the YouTube video description. Okay, good.
Yeah.
Let's see. Can we get back to
Stop sharing?
There we go. So the subject today is there's some new papers out. In fact, pop them up here. Emerging hemispheric asymmetry of Earth's radiation. And let me see. Let's see. There's another one. I just have, and then another one, actually with some of the same authors. Observed trend in Earth's climate energy imbalance may provide a constraint for low climate sensitivity models, and that's like a uh-oh kind of headline there. So, but we'll probably start along with the emerging hemispheric asymmetry. And Liam, why don't you take it away?
Yeah, let me first. Okay. Screen. Yeah, I'll share it like this because then it's.
Well, you can pick a different window
lighter.
or do this one, whatever. Let me. Let's
remove.
Okay,
Yeah.
there you go. Okay.
Yeah, so this is indeed a new paper. It was published, I think, last 2 weeks ago, 1 week ago. And its lead author is Norman Loeb, and he was a co-author of our Global Warming in the Pipeline paper. And he's the head of the NASA Ceres mission. And we've covered that data of these satellites, for NASA satellites, in quite some detail in recent even weeks and the past years, because this is really a clear indication of how fast and why our climate is changing so rapidly. And indeed, it's called Emerging Hemispheric Asymmetry of Earth Radiation, and seems quite technical, and it is quite technical, but it is really crucial to understand what's happening here if you want to understand climate change and why it's changing now so rapidly and how it will change in the future. And that's also a reason, and we cannot stress this enough, that we really need to secure these satellites and launch more of these satellites to secure the data and also to increase the accuracy even further and have a higher resolution data to really see what's happening. And what they find is that, and we've seen that before, is that the northern hemisphere is brightening faster than the southern hemisphere mainly, and then that's really the main finding. And that's this is a graph I made, and I'll show you some of the graphs from the paper later. This is the data from these satellites, and it shows the northern hemisphere energy imbalance. So how much? So this is 240 to 242.5 watts per square meter about. So there's a lot of energy, of course, globally, day and night average, for the 48 months, so 4-year running month average. So there's that's an indication of how much sunlight is absorbed globally on average. And that's a lot of energy, but of course also a lot is radiated back to space as infrared. So and that's the red line. And until 2014, the northern hemisphere was absorbing less sunlight than it was radiating to space. So of course, but that has, as you see here in the data, you see that there's a big increase in how much sunlight the northern hemisphere is now absorbing, and that increase in outgoing long wave radiation, so heat radiation. Every body that has a certain temperature radiates heat, and that increases with the temperature increase. exponentially. So if the temperature increases of the northern hemisphere, it will also increase the amount of heat radiated back to space. But it cannot keep up with the increase in absorbed sunlight, which is why the heat accumulation over the northern hemisphere is increasing.
The energy imbalance.
Yeah, that's energy
And I
imbalance.
think, by the way, it's
Yeah,
important to
sorry.
mention here that just for kind of climate science education, that when you talk about outgoing long wave radiation, as you mentioned, that's the heat. So you shine light on something on the Earth, and it heats up, and then it gives off heat. It radiates it out to space. And when everything's fine, the amount coming in, the amount going out are equal, and everything's fine. But what's interesting is
It is in balance. Yeah.
yeah, it's in balance. But when the temperature goes up, when the Earth's temperature increases and it starts to radiate heat away, it radiates heat away at the fourth power of the temperature. And
In Kelvin.
this is actually one of the main controls for keeping the Earth system in balance, is this fourth power of the temperature. So when the Earth heats up, it really starts radiating a lot more energy away. Now, we're still trapping heat faster than that, unfortunately, and that's what's causing this energy imbalance. But I just thought it's kind of really interesting to note about the fourth power aspect of the heat radiation.
Yes. And what's this might seem like a very large number, this 242 watts per square meter. But you have to, and then if you look at it from this scale, like you think this is not a big increase, but with temperature, of course, we also usually don't have the reference of 0 degrees Kelvin, right? Because it's 273 degrees below 0 degrees Celsius. That's the 0 Kelvin is, and so that's what you have to take into account. Of course, that we live on a planet that's about 15 degrees Celsius on average globally, above 0 in degrees Celsius. But if you add those 273 degrees Kelvin, then these watts per square meters make more sense, maybe. So I think that's. And then so here I made a graph where you see the reflected sunlight, again the northern hemisphere albedo, which is the percent of sunlight reflected back to space, and then the change over the past 20 years. And then you see that the albedo, so the reflectivity of the northern hemisphere, is now lower on average over the year than the southern hemisphere was 20 years ago. And that, of course, the southern hemisphere is much more ocean. So, and of course, these dark oceans absorb much more sunlight. But there's also a lot of cloud cover over these oceans. So I think this is quite striking that and this, of course, this line looks different from this line, but the axes are the same, the y-axes are the same. So yeah, you can see that there's something is happening, and we can see that here as well, where the northern hemisphere is now absorbing more sunlight on average over the year. So average over the entire year and day and night globally, or over the hemisphere, sorry, over 255 trillion square meters, so half of the Earth's surface. It now absorbs more sunlight than the southern hemisphere does. So even you might sound a bit contradictory because I said the albedo is lower, or I just showed that the albedo of the southern hemisphere is still lower. But of course, it also depends on when the albedo is low. If it's during the winter, if it's during the hemispherical winter when there's not a lot of sunlight, that matters less than if it's during the summer. And we see that also that especially during the summer, the difference is even stronger. So that's why this this increase is stronger than over the southern hemisphere. So the increase is stronger, and now even the absolute value is higher.
Mm-hmm.
And it wasn't. It was before at the start of the century. It was lower, but still the imbalance of the southern hemisphere is higher. So the southern hemisphere accumulates more heat than the northern hemisphere does.
That's what has land, right, instead of water, and so land is hotter than the water, and therefore radiating more heat. Is that the
yes,
main
indeed.
driver?
So the northern hemisphere is hotter, so it radiates more. Indeed, if you look at the red line, it radiates more heat to space. And also, yeah, I'll get to that. But there's heat transported from the southern hemisphere to the northern hemisphere, mainly through the Atlantic Ocean.
The AMOC, the famous Atlantic
Exactly.
meridional overturning circulation.
Yeah.
That's transporting. So that let's summarize that, because that's a really important concept. So there's more heat being generated in the southern hemisphere. One of the main reasons is it's darker there because there's far more ocean in the southern hemisphere than there is in the northern hemisphere. Dark ocean absorbs heat. There's other factors like clouds, which are very important, I guess, in this paper as well. We talk a lot about clouds being a compensating factor. But when you are generating more heat in the southern hemisphere, it wants to go somewhere, and it gets to the northern hemisphere through the AMOC as one of the mechanisms, and other circulations, and that it brings that warm water from the tropics up to northern Europe, for example. So that's what's happening here, and why that's one of the main reasons why there's an asymmetry. But the change over the last 25 years is interesting, because the changing pattern has something to do with our own actions involving aerosols.
Yeah,
So we'll get to that.
and not just that, but indeed that's I'll get to that as well. And I think I'll just show you a bit more of the data. So because it's really, I think this is really insightful. These y-axes are the same, so you can really see that the southern hemisphere is absorbing much more heat than it radiates to space. So the energy imbalance, and it has been that, most likely has been like that for the past decades as well. Much of the past century, most of the heat accumulation happened over the southern hemisphere, and then the heat was transported to the north hemisphere. But of course you have to realize that now this is changing, and it will impact the climate. And this is a different way to visualize it. Here I visualize the energy imbalance. So here I show you the sort of radiation fingerprints, as we call it, where you see the long wave and the short and the sunlight. But here you see just the value of energy. So you see
the difference between those two, basically.
Yeah. So indeed, it's like absorbed sunlight minus outgoing heat radiation is the net, and the energy imbalance. That's what the energy imbalance is. And if that's positive, you will have global warming. And that's really, I think, I wish there would be more coverage on this to help people understand like what drives climate change. More heat accumulating in the system, and then and now we have more heat accumulating in the system faster, which means climate will change faster. It's really that simple in many ways, right? But I think, I think it helps really to understand these basic units scientists talk about when they talk about energy. And you see, so energy is now also accumulating faster in both the northern hemisphere and the southern hemisphere. But the increase over the past 20 years was higher over the southern hemisphere. Over the northern hemisphere. The increase over the northern hemisphere was about 1.1 watts per square meter. So then we call that net flux. So it increased from about minus 0.3 watts per square meter to positive 0.8 watts per square meter, and that's so really a lot of energy over this enormous surface. And then the southern hemisphere, it increased only by 0.8 watts per square meter, but the value is higher, of course. And that's and then this is from the study. From this new paper, where they again absorb sunlight, absorb solar radiation, outgoing long wave radiation, and the net effect: the southern hemisphere in blue, the northern hemisphere in red, and then here this is the northern hemisphere minus the southern hemisphere, and then you see that there's this strong trend, as the data I showed you also indicated that there's a very strong trend in the northern hemisphere absorbing more sunlight faster than the southern hemisphere does. And there's also a trend in the outgoing long wave radiation. Of course, the northern hemisphere is warming faster than the southern hemisphere, also because it's absorbing more sunlight, and then it's warming faster, and it also radiates heat more faster than to space, but not as much. This increase doesn't keep up again with the absorbed sunlight trend, which is also why the energy imbalance of the northern hemisphere is increasing faster than the southern hemisphere. And these are the decadal trends. And yeah, I think it's a bit technical, but it looks a bit like the graph or the table I extrapolated from global warming crossing points. But I think maybe this is even more important in many ways, right? Because this is the heat, and global warming is important, but it's also really very much about how much heat accumulates in the system, how rapidly, and where does that heat go? Does it go to melting of ice, right? Even if you don't have global warming, but if you have faster melting of the ice sheets, that, for example, for a low-lying country as mine, the impacts might be even greater than if you would have faster global warming. So and that's really that basic physics of heat. If you understand that, yeah, this shows how fast this heat accumulates, and then you can use that data to estimate how the near term impacts. And here, I have a few more graphs here. This is again a different way of showing the data. So how it changed from 2004, again the 4-year average from 2004 up to 2004 to today, and there you see again a very big increase of over 2.2 watts per square meter, which is really an enormous amount of accumulated in energy.
Right, we can do the Hiroshima bombs per, let's see, 0.6 is 400,000. So 2.4 would be 1.6 million Hiroshima atomic bombs per day, every single day. That's how much energy. 2.4 watts. Now you're saying this is 1.1, so
2.2. Yeah, no. So the
2.2
absorbed sunlight increased by over 2.2 watts. Again, it's off the chart.
About 1.5 million Hiroshima atomic bombs every day. That's roughly how much energy that is equal to.
Yeah, and that's also our paper with led by James Hansen, where Norman Loeb, who authored this paper, was also a co-author of, by the way. That we showed, of course, that this what was I going to say? This 4 watts per square meter global greenhouse gas forcing, and how this compares to this level of absorbed sunlight. As you mentioned, it's millions of over a million Hiroshima bombs.
Yeah.
But yeah, and there's this shows that because there's a big increase here, that there's still a lot of global warming in the pipeline. That's what I want to say. That that's what this data shows. And of course, we we wrote that paper back in 2021, 2022, and the final paper was published in 2023. But then it has only increased, especially over the Northern Hemisphere. As more data came in, you can see that it has increased a lot.
Right.
The amount of absorbed sunlight has increased a lot over the past years since we wrote that paper. So it's maybe it could be even worse, of course, than we thought it, or than we feared it would be, because we, of course, at the time we had limited data of what I'll get to of the impact.
So it started shooting up in 2020, around 2020, 2021. Can you tell us what major event happened in 2020 that could possibly cause this temperature, this increase in absorbed solar radiation?
Yeah, so especially over the Northern Hemisphere oceans, of course, and wait, is this graph? Yeah. So this graph shows you, and then I'll answer your question. This graph shows the effect of aerosols, which are particulate air pollution, in causing cooling. So they were causing, of course, global, as those who've been watching this show, I hope now know that aerosols cause some cooling, and that those have been especially being emitted over the Northern Hemisphere. So the IPCC best estimate is that there's about half a watt, or it says
half a degree.
I hate how they wrote this down, because nobody can read this right, but it says 0.66 degrees Celsius of global cooling, and this mainly says the Northern Hemisphere was cooled about 1 degree Celsius, and it almost looks deliberate the way they wrote this,
right.
To make it not understandable.
So they said, just so people maybe they can't see it, it says minus 6.6 times 10 to the minus 1. So that's the same as 0.66. Could have just written it that way, 0.66 degrees of cooling globally. And then they said Northern Hemisphere, 9.7 times 10 to the minus 1, which is 0.97, about 1 degree of cooling. And Southern Hemisphere, minus 3.4 times 10 to the minus 1, or about 0.34, about a third of a degree.
Yeah,
of cooling. So big difference.
Yeah, and I think you lost half the audience now, right? If
right,
because it like people don't draw. Yeah, even degrees Celsius is hard to relate to degrees Celsius of large regional warming, or cooling. But then if you write it like this, I think very few people can relate. But as this shows that there's, especially, of course, the blue means cooling due to aerosols, and that mainly happened, of course, over the Northern Hemisphere, but also over the North Pacific. We've been talking about that a few weeks ago, that the North Pacific is rapidly warming now that air pollution is being rapidly reduced over the oceans and over China, and then of course the North Atlantic. This means conflicting signals that there's uncertainty, and that's because, of course, there's many things happening here, like natural aerosols and the AMOC, and etc. So that's less straightforward than the North Pacific. But yeah, if you reduce air pollution, as we have been doing over the past decades, it's the signal we would expect that to see is first is a decrease in how much sunlight is reflected back to space because of a decrease in cloud condensation and decrease in cloud cover, and then faster warming, resulting in even less clouds, especially over these large stratocumulus regions, and then seeing even faster warming. And as George told you then, that we also see these shifting rain bands and cloud bands, where
right.
and that's what. Sorry.
Well, I just kind of just reemphasize what you're saying, and maybe is that there's really three things happening that change the absorbed solar radiation. One is that there's less ice. Ice is white and reflects a lot of light, and as glaciers melt and Arctic sea ice goes away and that kind of thing. Um, uh, but that's actually relatively small. It's important, but relatively small compared to what you were just talking about, which is aerosols, both reflecting the sun away and causing clouds that reflect the sun away. So as you decrease aerosols, you get less reflectivity from the pollution itself, and you get less clouds. So you get more absorbed solar radiation. And then, as you also mentioned, George Salutis on our program talked about how global warming itself, just the Earth getting warmer, seems to decrease cloud cover. So another way of saying that is global warming means less clouds means more global warming. And so those are three main effects that are changing the albedo or the reflectivity of the Earth. But we don't keep going there.
Yeah, yeah, and then I think that's also what this new study covers is that uh, because of course um, these changes happen. There's a difference in these radiative changes over the different hemispheres, and as I showed you, there's also that means that more heat is accumulating faster over the northern hemisphere than the change that we see over the southern hemisphere. That we expect then that there was also a change in how much heat is transported from the south to the north. And this is from the ECMWF reanalysis data where they show the amount of heat transported through or the anomaly or so the change in how much heat is transported through the top 1,000 meters of the Atlantic Ocean northward.
So what is it saying? So it's going from starting around 2000 or so seems to be the dividing. The red is it's giving off heat, and the blue is it's
No,
what?
this is the delta. So this is, sorry, that means change. So these are the absolute values. So heat
Okay.
transported northward through the Atlantic Ocean, so the AMOC
Mm-hmm.
mainly, and this is the change. So you see that there's a decrease in how much heat is transported northward in this reanalysis, and there's
Wow.
and there's different many different lines of evidence showing
And this is a slowdown. This is a
yeah.
slowdown in the AMOC.
Yeah, so this is
Dramatic.
a decrease in heat transported, but it's
Oh.
this is also I could also have shown the graph which shows it in sphere drops, which is million cubic meters per second of water transported by. But this is the water has a certain temperature, and if you transport that water northward, of course, and then it to colder regions, it brings heat to those regions, and that you can also um, use the unit petawatts, which I think is sorry if I get this wrong, 1 to the 15th power joules per second.
That's a lot.
A lot of energy per second transported northward by these oceans. And I think I have a table here. Where is it? Yeah.
There we go.
Yeah, here it is. So the strength of the AMOC is about 17 sphere drops, which is 17 million cubic meters per second, which is about 1 petawatt. So that's the baseline without the change. And then that's a million times a billion joules per second, or 32 zettajoules per year, or 4 watts per square meter northern hemisphere equivalent. And then we get back to this increase. If I say 4 watts per square meter of northern hemisphere energy equivalent, that this is 2.2. So that's about half of the amount of heat transported by the AMOC northward, or over half, has now the northern hemisphere is now absorbing more sunlight over the past 20 years. because do you understand that? Is that clear?
Yeah.
Yeah. So because so that's about over half a petawatt of energy is now more absorbed over the northern hemisphere.
And going back, I mean, this graph, by the way, I think it's a really important graph showing the aerosol cooling versus the latitude. And it's showing that there's a lot more cooling going on in the northern hemisphere. And that makes sense because one thing about aerosol, so CO2, when you release it, it gets spread out over the entire globe. But aerosols or pollution, they only last in the atmosphere for about a week. So they don't have a chance to sort of mix in throughout the whole atmosphere, and they're more local. So when there's pollution in China, for example, from their coal plants and everything like that, it tends to hang around China and cool off China, and by the way, kill people through the pollution as well locally. So it's more below, and we're kind of seeing that here. Most of the aerosols are released in the northern hemisphere. That's where most of the industry is. That's where most of the coal plants are, the ships and everything. And we're seeing more cooling. So it all makes sense. But the thing that I don't think people appreciate is the amount of cooling is very significant. Even in this thing, it's showing in the northern hemisphere that it's like 2.5 degrees of cooling in the northern part of the globe, but that's a lot. That's crazy.
Yeah, and that's the best. That's the best based on the best estimate of the IPCC, and after we show that in our recent studies, and I think more and more start to acknowledge that, is that the best estimate of the IPCC should be considered a very the lowest estimate. It's
Half
likely about half more, so it's about 50% more. So the climate is about 50% more sensitive to a given forcing, whether it's from greenhouse gases or aerosols, than the IPCC estimates.
Mm-hmm.
And that means that it's not it's not 1 degree of northern hemisphere cooling. It was 1.5 degree of northern hemisphere cooling, which is what there's also this uncertainty range that it's could be like
Oh, wow.
over 3 degrees Celsius of cooling over the higher latitudes.
Wow.
And of course, then if you mitigate this cooling without addressing greenhouse gases, these are the latitudes where all the permafrost is and all the methane hydrates and all the boreal forest and then if you that's already what we're now starting to see, that if you reduce this air pollution, you have these feedbacks where the taiga forest, the boreal forest starts to burn, and the peatland starts to warm and to melt, and the permafrost starts to be less permanently frosty, and release its CO2 and methane, and then of course then it will be very hard to reduce the greenhouse gas concentrations, it will be very hard to keep the rate of atmospheric increase stable, let alone decrease, let alone reduce the atmospheric concentration, right? If the feedbacks start to emit more carbon, and the ecosystem start to emit more carbon because all these feedbacks and because all these forcing change. So this is really important, and I think for these regions, it's so for some of these regions the effect of aerosols is still more important than the effect of greenhouse gases in determining the regional temperature.
Yeah, this is the Faustian bargain that Jim Hansen talked about. We release CO2, which warms the Earth for hundreds to thousands of years, and we cool it using pollution that lasts about a week. And then as you start to clean up your fossil fuel pollution, part of that fossil fuel pollution is the CO2, of course, and that's great to cut that out. But at the same time, you're cutting out the aerosols that are cooling the Earth, and that effect happens almost immediately as you start to cut back, and you end up with warming. Now, the quote good news is if we actually cut back on methane emissions as part of our fossil fuels, that that only lasts in the atmosphere for about 15, 20 years. And if we actually cut that out, that would offset the somewhat offset the increased warming we get from less aerosols. But the CO2, you can cut it out today, and the amount you put up there is basically going to warm the Earth for hundreds to thousands of years. So only the methane is, and I guess there's some other short-lived greenhouse gases. But that's a whole other thing to get into. But the bottom line is that if we're underestimating the cooling of aerosols, which the IPCC seems to be doing, that means there's more warming in the pipeline than we think as we clean up as we go to the energy transition, as we phase out fossil fuels and therefore phase out aerosols. And keep in mind, we're not phasing out fossil fuels. We're at record highs. But what we are doing is cleaning up the pollution. Now, this is really bad pollution. It contributes to the deaths of 8 million people a year, which is 1 in 5 deaths. So it's not a little thing in terms of health consequences. So, but as we clean it up by having low sulfur fuel on ships, by putting sulfur scrubbers on coal plants, but first in the US, like in the 70s and 80s, and then in China now, as we do that, we're cleaning up the aerosol pollution, but we're not cleaning up the CO2 pollution and the methane pollution because we're not lowering fossil fuel emissions. And we're just cleaning it up. And therefore, more of the warming from the fossil fuel emissions is getting through, and we're getting less cooling from the aerosols. So we're sort of, I mean, it's good from a health point of view, but not good from a climate point of view.
Yeah. Yeah, and so we'll see faster warming, likely even faster warming than any of the scenarios or models shows, right? And I asked one of the co-authors of the paper we're discussing now to attend, Gunnar Meyer. I hope I pronounced his name correctly. He's from Norway. But he couldn't attend, but he will join Climate Chat later. And I think I would also really like to talk with him about this other paper which he led, where he showed that this is the NASA series data again, the satellite data, and these are the outputs from the models. Is shortwave, which is mainly like absorb sunlight, and here's the long wave, which is like the outgoing long wave radiation. And you see that none of the models capture what's happening and what the satellites are seeing, right? So that's and you can see that visualized in different ways. Here you can see it in watts per square meter per decade of energy, of the energy imbalance. Again, here is in white the NASA satellite data, and these are the models. So, and here again you see the NASA satellite data is higher than any of the models. So that's why we should assume the worst and prepare for the worst, that we might indeed, as we discussed, I think was one last week or the week before, 2 weeks ago,
3C
that there's a non-zero chance that we might see 3 degrees Celsius by the half of the century, right? And even if, I think it doesn't matter that much if the chance is 1 or 5 or 10%. The chance, there's a non-zero chance, and we better assume that it will happen, or try to make sure that it doesn't happen.
And even, by the way, if it doesn't happen in 2050, but happens in 2060 or 2070, I mean, okay, I won't be around, but my kids still will be, and obviously most of the younger folks here are going to be around for a long time. 3C, whenever it happened, by the way, forget 3C, 2C, which we're going to have probably in the 2030s, is going to be quite devastating to agriculture and in terms of extreme weather. Look at the extreme rainfalls that we've been having with just 1.5 degrees of warming on global average. And as averages go up a little bit, the extremes go up a lot. And that's what extremes of heat waves go up a lot when you increase the temperature a little bit. Extremes of precipitation go up a lot as you increase the average global temperature. and other kinds of things. And then impacts on agriculture, as I mentioned, and drought and everything. So, I don't know, there's nothing magic about the number 2050, but if we're
Yeah, for
headed for
sure.
3C, which is really what that's all about, and what this is suggesting, uh, it should be the biggest story on. I know there's a lot of bad stuff happening politically in the United States and around the world right now, and yeah, it's near term and whatever, but this is still a bigger impact on everyone's lives and going
Yeah,
forward.
yeah. That's like I don't think 5 generations from now people will think the most important thing that happened in 2025 were some discussions about the Epstein files, right? I think,
Yep.
and it's yeah, and yeah, it's
And this is, and we've talked a lot about, I mean, we're getting a little off track because here we're talking about climate science data. But one of the things we talk about on Climate Chat quite a bit is the human psychological problems in dealing with long-term issues, right? And
yeah,
Epstein files are something exciting and shiny object, and we pay a lot of attention right now. Yet this looming monster is in front of us, not far away, by the way. We're talking, 5, 10, 20, 30 years kind of thing. And we know it's coming. There's the data. No one is talking about it. It's not on the news hardly at all. And it's, in fact, the opposite in many ways, right? Denial is very strong. It's kind of crazy. Anyway, we'll continue to cover that as a subject on Climate Chat, the psychological as well as the sort of climate science aspects.
yeah, yeah, and I think that we can talk about more, but I think that, yeah, there's more about the AMOC. We've discussed it already before.
Well, yeah,
Um,
and
how aerosols could work keeping the AMOC relatively strong, and that if the AMOC stops, Earth energy imbalance will increase further, and that's likely will increase sea levels more. Yeah, I think that to me this is always yeah,
it's
from
fine.
130.
It's fine. Nothing to see here, as I say.
Yeah, this from 130,000 years ago, of course.
Do you have your little "It's Fine" doll there that we can show everybody?
Yeah, where
Is it on by your desk? No?
is behind
Oh,
me?
it's right behind you. Is that it behind you? Is that the "It's Fine" guy? Yeah, there he is. Okay. No, the house is on fire, but it's fine. It's all fine. Don't worry about it. So, one thing I wanted to show is, let's see, I think it's, let's see, no, that's, okay.
Hmm?
Oh, you have the screen share. Okay. So but there's the other paper. Let's see if I replace it
Should I
as a
stop
screen
sharing?
share window here. There we go. Now we should. What happened?
Oh, sorry, I stopped sharing. Here you are.
Okay. So this is another paper by some of the same authors. Observed trend in Earth energy imbalance may provide a constraint for low climate sensitivity models. And we might talk about this, do a whole show on this later, but later in November. But in the meantime, I think what's important to say here is that looking at this asymmetry, and then they tried to plug it into the models and say, okay, let's replicate this asymmetry. And they said, okay, well, if we use models with low climate sensitivity, and we did many programs on climate sensitivity recently, and how it's, as Jim Hansen says, and you were co-author with him on this paper, that the climate sensitivity is like 4.5 degrees, not 3 degrees as the IPCC assumes, and that's 50% more, which is a BFD, as they say. And Jim Hansen gave 3 different ways that we know this is right. One was looking at ice age data and saying, well, it cooled more back then, and therefore that means the climate sensitivity is higher. Also looked at what we're talking about today, albedo, but he looked at it for the whole Earth. And when you do that and you see that the Earth got dimmer by 0.5% over the last 25 years. You also come up with an ECS of 4.5 degrees. And the last thing he did is look at the current temperature spikes and the shipping pollution changes and all of that kind of stuff, which you helped with. And also came up with 4.5. Now, these authors are taking the asymmetry and plugging it into climate models and using different ECSs to see, and they say they can't replicate it if the ECS is too low. I think below 2.5 C.
Yeah, that was said. That's one of the figures I shared was from that study, from this study.
Yeah, but and so now they're not saying. I don't think they're claiming it's 4.5. I mean, they didn't like calculate that, but they are saying that their studies rule out lower ECSs, which suggests, obviously higher ECSs. So there's a lot of evidence that climate sensitivity is more than the IPCC is assuming.
Yeah,
and that means there's more warming in the pipeline.
And
we're seeing it. It's not like some future thing. In the last few years, we've seen the effects of this higher climate sensitivity.
One of the things, and I cannot quote them by heart now, but one of the things they say why they exclude, or why they think they can exclude the lower climate sensitivity estimates is because they also they assume I think a doubling of the impact of aerosols, and even then the low sensitive, or the low sensitivity models didn't come in range, something like that. So
Yeah.
even by taking into account a very strong aerosol impact, and so that's why they excluded. They thought they estimate they can exclude them. I think that's how. But let's ask Gunnar for more information on that when he comes on.
Okay. So maybe we should move to question. I don't know, Stacy, if you're ready. If I see you in video, I'll bring you online there. And but if not, there I have some pinned comments here. Well, let's see. Here's a question from Daniel. Do we know why the poles get warmer faster? Is there a curve linking temperature and Earth energy imbalance? Thank you all. So I think the first one is actually it's a little different. There's a difference between the Arctic getting warmer and the Antarctic. And the one reason that the poles get warmer faster than the rest of the Earth, well, the Arctic does, is because you're replacing highly reflective white sea ice, and that's important that it's on the water ice. It's not on land. The Greenland is on land, and Antarctica is on land. So when we decrease the amount of Arctic sea ice, you replace reflecting white ice with dark absorbing blue, and so therefore that effect is very powerful, and is one of the reasons why there's something called Arctic amplification, and that's why the Arctic gets warmer faster than the rest of the planet. With Antarctica, it's actually very, very thick ice on land, and it's going to take a long time to melt that before it gets to the land. So anyway, that's a quick answer to that part. Leon, do you want to answer? Is there a curve linking temperature and Earth energy imbalance?
Curve linking.
I mean, like a graph that shows. I mean, you just have to look at the temperature graph of the Earth getting warmer, and what's driving that is the Earth energy imbalance.
Yeah,
so that is.
Let me get one graph. It'll take me 1 minute, but I'll get it up.
Okay, and next we'll go to Eli, who might have a question or a comment, and then we'll get back to. And if you do have a question for the live chat here, just try to put question in front of it so it's easier to spot versus everything else that we see here. And while you're doing that, let's bring Eli in. Hey, Eli, welcome.
Hi, Dan. Thank you. Hi, Leon. Comment and question. There was a paper out on the 1st, and it just got attention in the news a couple of days ago about methane seeps in the Ross Sea around Antarctica. Specifically, before they had only observed one around Antarctica. Now they're seeing several of them in places that they had surveyed before. So it's not like, well, it was there all along and they missed it. It's new. It's recent, and presumably it's driven by some of the other changes we've made to the climate, which of course is amplified. Climate disruption is amplified at the poles. So since you're kind of closer to some of the modeling issues, I wonder, we're talking about different things that haven't been predicted properly, which, just from basic physics, we know are coupled. Is there any effort to try and in a faster time frame than the IPCC operates to try and reconcile these multiple adverse trends, which would seem to potentially operate synergistically to get a better picture?
Wait, Dan, what you were showing some video.
Oh, this is from the article. This is what Eli's talking about. The scientists discovered something alarming seeping out from beneath the ocean around Antarctica. And basically, it's how scientists are finding more and more methane seeps. So this little white area is methane. And then you can, not in this one, but in the other video, you can see little bubbles coming up every few seconds. And those are methane bubbles coming out from the ocean. They're saying they're discovering a lot more of them than they've seen before. Although it's as
well, there's that plume. There's that plume right there. I think that's
yeah. But
that's
you asked Yatsuko a question. Were you asking me a question?
Well, I think his question was, look, there's all these things that are underestimated. Earth energy imbalance is worse than we thought. That maybe the methane is leaking faster than we thought. And all of these are going to be synergistically coming together to cause more warming, which of course will then feed back and cause more problems and more warming. So I guess that was the general question. Is that right, Eli?
Yeah, pretty much. Is there any attempt to at least get an idea of what the upper and lower bounds on what the coupling can be, and ground that in the actual recent observations of changes in ocean heat transport, changes in Earth energy imbalance, increased methane concentrations? We know that the concentrations have been going up, and part of the point they make in this article is that, well, this could be part of the discrepancy in terms of sources that hadn't been identified. So there are a lot of things going on. They're mostly pointing in the wrong direction, and it doesn't seem like the models, the top line models, really have a handle on many of them.
Yeah, that's true. Yeah, so of course we wrote a paper trying to show at least more of these effects and take into account more of these effects, and basing that on all these different lines of evidence, and then we came to the conclusion that the climate is very much likely more sensitive to our forcing, so aerosols and greenhouse gases mainly, than most thought, right? And then of course, as we already covered, that will also cause more feedbacks to come into effect. And yeah, I think the climate system is very, very complex, and we will never understand everything, and we'll not. It's many things are unknowable, so we cannot predict to any certainty which feedback will come into effect when. And but we do have some insight in in what we can do to mitigate it still. I just want to go back to the previous question.
Mhm.
Then
Okay.
stop that
Oh,
video.
yeah, okay, wait a minute. Let's go to here. There we go.
So
Okay.
that's where am I? There.
Oh, right. Okay, let me pull up the other question.
So this is from a recent paper, and Earth's energy imbalance more than doubled in recent decades, and this is mainly uses the same data from these NASA satellites, and again the point where our capability to observe the Earth's energy imbalance and budget terms is threatened as satellites are decommissioned. So we really need more satellites. I cannot stress that enough. And these are really many of the world leading scientists co-authored this paper. So I think I think it's quite. I think we can say that the scientific consensus has reached more or less the level of accepting that Earth's energy imbalance is more than doubled. If you know some of the names here, I think that these are really many of the world leading climate scientists who co-authored this study,
including Andrew Dessler, who we'll have on in a couple of weeks. That's great.
Yeah, Andrew Dessler and Veerbhadran Ramanathan, and Ed Hawkins is there, and I could name, I could call out all these names.
Okay, this is great. And back to the question.
Yeah, back to the question.
Energy imbalance is what causes the temperature to go up.
That's why I was getting this paper out. Well, this is again the same data showing this trend of 0.45 watts per square meter per decade increase in the Earth's energy imbalance every decade. That's the blue line. The energy imbalance increased over these 24 years by about 0.45 watts per square meter. And then during these El Niños, it's a bit lower, as we now experienced as well, even it was very high in the beginning of the El Niño. But then to answer this question, this is from models using low emission scenarios, where you see here in red the Earth's energy imbalance. And even if the Earth's energy imbalance goes down and reaches peak in these climate models, right? This is just indicative of what we expect, what the models expect, or to when the peak of the energy imbalance is reached, after which or how long it takes for the peak of the global surface temperature to be reached. And that's in 2070, so that's about 40 years later. So even if you start reducing Earth's energy imbalance by reducing greenhouse gas emissions mainly, especially methane as Dan mentioned, then it will still keep getting warmer for decades.
I don't understand this, because if the Earth energy imbalance is positive, if it doesn't go to 0 or less, I don't know why the temperature wouldn't keep going up, even at 0.5.
Because there's still a lot of
adding more heat than taking away. Go ahead.
Because there's still a lot of ice to melt, and there's still a lot of deep oceans to heat up. So
okay.
And so the colder ocean water from below come up, and then and the ice will keep melting. Right? If you would have a sea level rise graph here or an ice melt graph, you would see that there's still a lot of heat. If there's still a lot of heat accumulating in the system, of course, that's being directed somewhere, as you're right. But that's very much also being directed to melting of the ice sheet. So, and that really takes a lot of energy to melt ice.
Okay. All right. Well, that's not really good in the long run, though, is it?
Not for us here, no.
All right, the Faustian
bargain. And it really, I should really stress again that if you look at this value here, it's reaching over I think here's it's
Okay.
about 1.3 to 1.5 watts per square meter. So that's much higher than in these models, right? So the Earth's energy imbalance is now closer to 1.5. So we won't stop at 2 degrees Celsius.
Okay. All right. Let's turn that off and bring Stacy in here because Stacy's now on. Hey, Stacy.
Hi, how are you? Sorry, I was
Hi.
All right.
running a little behind. I well, thank you for talking about this. It's also very important. I was really shook by the article that Eli sent that he discussed the methane leaks in Antarctica, because unlike the Earth's energy imbalance, which is important but somewhat abstract, especially, Leon, you called it out when you said, yeah, you've now lost 90% of the audience because it's just not something that lay people tend to understand. Whereas methane leaks in Antarctica, I think even my mom could kind of get that, So it's much more material thing. One, I also
It
wanted
keeps
to make a,
surprising me, right?
what's
Because
that?
to me, I keep being surprised by that because, like, if you cook food, right, you add heat to your pan and you make the temperature go up so you can cook food. So everyone all works with energy every day, and but like how many people see methane hydrates bubble up, right? It's not something I think people grasp. So to me, it's quite surprising that the basic units to understand energy transfer are so hard for people to grasp.
I
But
guess it's the enormity of it, that when you're talking about something specific, like I see the methane coming out, where would that have come from? How would that have happened? It seems a lot easier to grasp than the energy for the entire planet. Yes, everyone understands the principles, but it's just too large. One thing I'll relate I am very late to the party. I didn't watch Game of Thrones when it first came out, but I've been watching it now. And it occurs to me that the White Walkers, if people have watched it, is parallel to climate change because instead of all the infighting, like we're talking about geopolitical issues, et cetera, in our world, in this world, they're doing this kingdom's fighting against this kingdom, this family's aligning with this family, much like we see in our political landscapes around the world and what people are preoccupied with. But the truth is, we all need to bound together, no matter what our beliefs are on all of these other things, because we don't stand a chance if we, as a species, the one that is most responsible and is able to move the needle the most, takes more responsibility for our planet.
Okay.
I did want to make a plug. This talk that you're in, this preventing
2
then the
degrees.
number 2 degrees. It looks very interesting. Leon is speaking right after him. Jim Hansen is speaking. The next day, what's his name? We've had him on twice. University of Chicago.
David Archer. Oh, David Keith.
Is
David
that
Keith.
him? I
David
think it
Archer.
was. I don't know. Shoot, maybe I got it wrong.
Solar
I don't
radiation
know.
management.
Somebody we've
David
had on the
Keith.
show is on, and then also friend of the show, Brian von Hertzen, is on a moderated panel on the second day. So if you guys have time, I would recommend tuning in. It's just 2 hours a day. It is free. You can sign up at preventing2degrees.org. And I think it is a worthwhile way to spend time. Oh no, it's Cornell. It's Doug McMartin.
Oh, Doug
Sorry.
McMartin. Okay.
Yeah, not David Keith, Doug McMartin. I knew it was someone
Talk
we
about
had.
solar radiation management. Okay.
Yeah, I highly recommend that. I've signed up for it, and I hope others will as well. And I would be remiss if I didn't say please like and subscribe. This is something that we do not say often enough, and it helps to get the word out and people are just lying. And it would be helpful if more people were able to hear this message today
And also leave
and other
comments
days.
on the regular YouTube video, because that also gets to the
Bumps it
algorithm.
up.
Yeah.
Yeah.
And
Um,
share. You can keep sharing this after the live session ends.
And
Mhm.
I have one like kind of related question. This is helping me with my an argument on LinkedIn. Has Hansen said any has Hansen said when he thinks we might reach 3 degrees? Like I know, the global warming in the pipeline, but I couldn't find anything that says, oh, like 3 degrees by 2050, say, like the German meteorologist has said. Do you guys know any? Does
I
he have
know he
any
said
dates?
he has talked about 2 degrees, and he
Mm-hmm.
has talked about how 2 degrees is catastrophic. So I don't recall him making a particular prediction for 3 degrees, which I don't know how important that is when you know when 2 degrees is happening, and it's
Well,
in
yeah,
a
I mean,
decade or so,
Yeah, the main points we have to avoid 2 degrees and 3 degrees at all costs. And well, of course, in our paper, we highlighted many ways that can help to reduce the impacts of climate change. And yeah, of course, most of those things are not being done. Carbon is not being priced. There's no global cooperation happening to work on clean, low carbon solutions, and there's no effective broad research being done on how to reduce the risks of sunlight reflection methods if they are if the world decides that we will use them, right? So we really need that research, and there's not just us saying that, and not just Hans saying that, but I think most of the climate research who understand that the rate of warming is increasing, and the impacts it will cause, understand that societies will get desperate and head for desperate solutions like sunlight reflection methods. And the worst thing we can do is not do the research before desperate societies cause more harm than good.
Yeah. And I think, by the way, one of the reasons that we're not so focused on 2 degrees is that, the Paris Accord and these other things said, hey, let's make sure we stay under 2 degrees, with this implication, which is false, this implication that 2 degrees would be okay, right? If the goal is to stay under 2 degrees, that implies that that's some kind of safe level, but it's not. The 2 degrees was picked kind of randomly 20 years ago or something. And then the more we learn, the more we realize that 2 degrees is really dangerous, and there's like many tipping points that we'll cross. By the time we hit 2 degrees and all this kind of stuff. Yet 2 degrees still stayed there, and one reason it stayed there is because you don't want to pick a number that's less than where you're at now, right? It doesn't make any sense, to people. They don't have a goal that is not achievable. They thought
yeah.
2C was achievable, but also, as Hansen says, it's not. I mean, well, staying under 2 degrees is not achievable. He said we're going to go past it, and first of all, we're not lowering our fossil fuel emissions, so
And
it's not all
as
you need to
Sun's
know, right? I mean, it's not like we're trying to stay under 2 degrees. If we were trying to stay under 2 degrees, we would have plans in place to greatly lower our emissions, probably ramping up carbon removal, probably preparing for solar radiation management. We're not doing any of those things. We're just talking about energy transition, where we're greatly, and this is true, we're greatly increasing solar power, for example, and wind power at a crazy rate. But the thing is, solar power doesn't stop climate change, and it doesn't cause climate change. It doesn't matter how much you have of that. All that matters is how much fossil fuel emissions you have, and we're not decreasing that. It's not going up a lot, which is good, I guess, but it's not going down rapidly, and it really needs to, for us to avoid really bad, like the 3 degrees and things like that. So we're not taking it serious. No one's taking it seriously in the world right now, and at the government level, a lot of talk about it, but it should be getting a hell of a lot more attention than it is. Okay.
So, and as Sunspot mentioned, we aren't, if we used a proper 1750 baseline, we'd already be at 2 degrees.
Yeah, I mean,
which
yeah.
I think is probably
Well,
accurate.
I mean, you gotta. It's sort of what is everyone using when they talk about 2 degrees? What does 2 degrees even mean? And I think the consensus now it's the 1850 to 1900 baseline. And you got to remember that when we started burning fossil fuels, we increased aerosols faster. I mean, remember CO2 is cumulative. So back then, the accumulation was tiny, but the aerosol, the smoke from burning all the coal and everything was huge. So the Earth actually cooled a little bit when we started the Industrial Revolution. And it wasn't until the 1970s when we finally put the Clean Air Act in place and things like it, started doing sulfur scrubbing and started cleaning up our pollution, that the CO2 signal just kind of steadily went up. The warming signal went up directly. So,
and I want to just
Go ahead.
thank Reese. He said that in January 2024, Hansen had a projection out to 2050, which shows 2 to 2.4 C. So back then, you're, and 3/4 ago, he was saying 2 to 2.4. I would think he might revise that now.
Well, that was the global warming, the pipeline paper, right? That was showing, the trend for warming had doubled.
That would double. So we published that
that was the end of 23.
Yeah, but the preprint we published in 2022, and that's before the global temperature trend really started to increase, and then we said it would likely increase because of the Earth's energy imbalance had increased. But yeah, I think it increased more than it's really on the high end of our estimate. So and that's a doubling of the rate of global warming. And again, I think it looks like it will. If I showed you the data, especially over the northern hemisphere, the net flux has still increased by 2 watts, or what was it? By over the northern hemisphere, it increased by 1.1 watts per square meter, and the level of absorbed sunlight has increased by 2.2 watts. So there should be a lot more warming in the pipeline because it's not increasing yet. And we are still increasing greenhouse gas concentrations at record rate. Tipping points are starting to fill over land, at least. And it looks like maybe India won't reduce its air pollution as fast as they were planning to, but other places are. So yeah, as Hansen called it, the Faustian payment is coming due. And
and I think the important thing to mention here again, which we talked about a lot when we talked about the 3C by 2050 show, and that is Gesundheit, is that you have this error bar, right? So you have this wedge that they were showing that looks like it's the rate of warming is doubled and we could hit 2.4. But if you had error bars above it, you see that it could be higher than that and lower than that. But the point for 3C is that it's so catastrophic that you just have to assume that's what's going to happen, even though maybe it's a 10% chance. I mean, 10% chance of your plane crashing on your way to your destination. You're not getting on that plane. But hey, 90% chance you'll be fine. It depends what, if it's a 10% chance you'll stub your toe, maybe you'll still get on the plane. But if it's a 10% chance you're going to crash and die, then you don't get on the plane. And so our point about 3C was that it was a possible thing by 2050. And by the way, it becomes a likely thing later in the century. And so these are totally unacceptable risks that we are blindly going down the path to accept without even talking about them.
I mean, not just that 1.5, we have not fully seen what 1.5, which is essentially where we
Right.
are, what that's going to do to ecologies and to vulnerable populations, poor people in cities that are going to get hotter and hotter. We're not ready for even 1.5,
Right.
and we should do what we
Oh,
can.
and also
to
long
avoid
term, we're on our way to 75 feet of sea level rise based on today's CO2 levels, not on the future CO2 level. It just takes a long time to melt all that ice, but we are melting it. And and the last time CO2 was as high as it is today, sea levels were about 75 feet higher than they are now. So yeah, so we might only get 5 or 10 feet, by the end of the century, which is still crazy, a lot of sea level rise, destroy most of the coastal cities. But we're really on a path for far more than that in the future. So we're just not, humans just don't care what happens more than like 2 weeks from now. So
No, they don't. And one thing Frosty mentioned, I think that speed is telling us it is in runaway, but we cannot scientifically prove it, so they won't say it.
um,
I
I'm not, no. And Hansen addressed this too. He at one point said we could have a runaway like Venus effect, and then he said, no, looking at the numbers, that's not true. But it doesn't really matter. I mean, what does it mean to be runaway? I mean, runaway means that
well,
the
we're
warmth causes more
accelerating.
warming, that causes more warming, and you can't stop. It's going to just keep going up. But that's, there's going to, remember, it is the fourth power of the temperature, which is very powerful. The control knob there. But the
Well,
point is that 2 or 3 degrees, which we're certainly on a path for now, and 4, maybe the end of the century, is that's all you need to know. You don't need to know about anything. You don't need to know about runaway. That's
well,
enough
yeah, but
to destroy
the
civilization.
the runaway that Hansen was talking about was evaporating the oceans.
Yeah,
Right.
right.
Effectively speaking, runaway that makes ecology unrecognizable is enough to worry about, and we can't rule that out at this point. I mean, 4 degrees.
The good news is
4
the
degrees
oceans aren't going to evaporate. The bad news is we're on a path to extinction. So, all right. So what if?
So
But not
Thomas
by
had
the way, I just want to make one note, but not by 2026, as Guy McPherson said. So people keep putting Guy McPherson in the comments. Let's have him on the show. Not going to have him on the show. He's a denier in the opposite sense that most climate deniers are. He takes the bad information, and there's, as we talk about here, plenty of bad information, but he just overemphasizes it and shortens the time frames. So he literally said in 2018, which is not a long time ago, that all humans would be extinct by 2026. And so let's not go too far the other way. I mean, it's bad enough as it is, as they say. And who said that, Leon?
I don't
The
know.
truth is bad enough. But the truth we're talking about here is pretty bad. And the sad thing is there's lots we could do about hopefully in the conference we'll be talking about it, that Leon's attending there.
Yeah.
But
so
there's a lot we
Thomas
could do, but we're not really doing much right now.
Thomas did have a question. Do we have to recalculate the carbon budget left for 2 degrees of warming now as the aerosol cooling has decreased?
Yeah.
Yeah.
So of course these carbon budgets don't really take into account aerosols or other greenhouse gases most often. Like they just say they assume in a way that those cancel out, or that they just don't consider them at all. They just look at the greenhouse gas forcing of CO2, and then that's what they determine the carbon budget on. And then in the fine print it says, so if the other forcings cause more warming, then the carbon budget might be smaller, which of course is the reality we are dealing with. Am I lagging or what is happening?
Oh, yeah, you are lagging, but that's okay. We
Okay.
can hear you though.
Okay. Yeah. So I think that's important to note that. What was I saying?
Yeah, don't worry
Yeah.
about the video.
So the carbon budget is much smaller than.
Well, I don't think there really is
read
any
in the
carbon budget.
papers.
There's no carbon budget left. I mean,
Yeah.
it implies, I mean, what is the word carbon budget? It implies that we can continue to emit CO2 for some certain period of time before we reach a threshold. But that threshold will, let's say 2 degrees, is going to be reached under any circumstances, and we would need to literally cut off fossil fuel emissions starting right now, which is not going to happen, or decrease it at such an incredibly rapid rate that it mean the word carbon budget, I think, is just not used properly. Anyway, okay, I think Leon had a
there was one more
building.
question at 11:22. The fish is dead said, is there already a prediction at which average temperature 2025 will turn out? If it's at or above 1.5, an acceleration of warming should be proven, right? There was no El Nino.
Well, it's interesting because Jim Hansen said that if 2025 is about the same as 2024, and it looks like it's going to be less than 2024 is my understanding, but there is sort of an El Nino kicking in too, so there's that. But he said if it's roughly the same, that kind of proves the ECS is 4.5, aerosols are much more than we thought, and all that kind of thing. So
I think
2025 is turning out to be pretty warm. It's one of the top 3 warmest years, I think.
Yeah, it will be about one, depending on the data set. I think ECMWF will be about 1.5. I don't remember exactly what Hansen wrote. I think if you look at it in detail, I think he said if there's an El Nino, or if there's if the tropical Pacific won't cool back down again, then we might reach similar temperatures as 2024, and that would indicate that that there's a very strong acceleration. But of course, we have now relative La Nina going on in the tropical Pacific.
Right.
If you look at the past, I think 2.5 years, there is no El Nino, right? There's especially the relative El Nino is like 0, because we had like 2 years of La Nina. Now we are at a relative La Nina. 2023 was still being cooled a bit by the previous La Nina, and then we had an El Nino which wasn't as strong as some thought, or some say that it was not as strong as 2016 or 1998, and still the temperatures were off the chart, of course. And then we're now, I think that the peak of the 2-year peak was at 1.6 degrees Celsius above pre-industrial.
But I do remember what Hansen said, because he said that if it is about as warm in 2025, is that it shows that we're right about the aerosols, because the way ECS works, you get the first third of the warming in the first 10 years, the next third in the next 100, the next third in the next 1,000 years. And if we're right, and the ECS is 4.5 instead of 3, then the change in shipping would still be pumping up more warming in this first 10 years, stronger than what everyone else thought. But what Leon and I think, I got to think. And so that was his point, I thought, about the 2025. So we'll see. But 2025 is turning out to be quite warm, and Leon said, it's happening even without an El Nino, and it's really showing what's going on here. Let's see. We have Eli joining. I'm gonna I think it's time to say goodbye here. I want to go through programming notes again. Eli, did you have anything else you wanted to say before we go?
Eli left as well.
Oh, he did. Okay. And actually, how do I turn this off here?
Hide.
Okay. There we go. All right. Before we go, let me repeat some important programming notes. And the first one is that there will be no climate chat next Sunday. Going to a memorial service, Leon's not available, so no program next week, October 19th. However, the following Sunday, October 26th, we have climate scientist Andrew Dessler, who wrote the rebuttal to the climate denial report that was published by the Department of Energy. Yes, we live in an idiocracy or upside down world, whatever is going on here. Anyway, a very in-depth rebuttal. And so we're going to talk to him about that on October 26th. On November 2nd, Wim Carton's going to be on, the co-author of a book, The Long Heat, which many people I know in the comments will be very happy to hear him. He's an anti-capitalist climate action person out of Sweden. He's against solar radiation management, so I think we'll have a really interesting discussion on that. And then following that, on November 9th, Jigar Shah, the former head of the Department of Energy Loan Office under the Biden administration, also co-founder of Generate Capital and a whole bunch of other things. He's been involved in climate as long as I've been involved and known him from way back when. And so we'll be able to talk about politics, politics in the Biden administration and things like that, as well as the Trump administration. And so that should be a really interesting discussion on November 9th. And then we also mentioned that Leon is giving talks at preventing2degrees.org. Prevent the word preventing, the number 2, the word degrees.org. And then you can listen to that. And other people like Jim Hansen are on there, as Stacey mentioned. So with all of that, thank you for coming this time. And we will not see you next week, but we will see you the week after then. And thanks, everyone. And thanks, Leon. Thanks, Stacey. Thanks, Eli. And
thanks, Dan.
All right. Take care, everybody. Bye-bye.
Bye.
Bye-bye.